Welcome everyone. This is the 55th DevOps Porto meetup. It's been a while. This is the first one we're doing in FEUP, the Faculty of Engineering at the University of Porto. The goal is to try to connect academia and companies. We often go from company to company, but we forget that there's work being done in academia that is worthwhile injecting into our day-to-day lives. It happens to be my alma mater. I dressed up on purpose today, but I'd like to make a call out. I know we have people here from Braga, from ISEP, from Faculty of Sciences. Talk to your professors. We'd love to do this there as well. I think this connection is worthwhile. I think we're doing interesting research, and it would be an opportunity to connect people, courses, because I left almost 20 years ago, and it's a little bit different now. DevOps didn't exist. So our mission is to build bridges between development and operations, but also between communities, companies, and the people that are part of them. You can find us in all the usual places. If you go to the website, you'll have the links to all the others. Yeah. I'd like to do a shout out to DevOps Days. So it's a conference that will happen here in Alphaville, Porto on the 26th and 27th of September. It's co-organized by the Lisbon and the Porto group. And we have two very cool keynote speakers, Charity Majors and Mark Schwartz. And a very nice program. I really suggest people to sign up and go. Monday and Tuesday.
But tickets are sold out, right?
I think there's one left. The last time I asked.
I'm not sure. I think that's like one or two.
I think there's like one left. If you have problems, maybe someone will drop out or something. I don't know. It's worthwhile checking out though. I think it will be recorded as well. So today, the introduction. That's me, and then we'll move to Philippe. Philippe is a professor here at FEUP. He'll talk a bit about science and engineering. And then we'll do a round of lightning talks with recent graduates from this school. We'll talk about patterns in the first half, DevOps patterns, then monitoring patterns, service mesh patterns, and then we'll go into tooling, and we'll talk about Dockerlive and Hermit, two tools that they developed here to enable workflows. And then, if there's time, we'll do a short Q&A, otherwise we'll just go hacking. Thank you. You're up. Thanks.
So, hello everyone. Like Miguel said, my name is Philippe. I'm a professor here at FEUP. I teach topics around software architecture and design, agile methods, DevOps. But today I'm not going to talk a lot about what I teach. I'm going to be talking much more about the topics that I'm researching within the big umbrella that is DevOps. And one thing I thought when preparing this presentation was, well, I'm not sure that in the audience that I'll be talking to, everyone knows what science is, what research is. And so I asked Google, and Google told me that, well, that's science, this is engineering over here, which is kind of funny, but not really accurate, I'd say. So I'm going to try to explain it with this other figure over here, okay? So I'll start by trying to explain what science is. And that's when you look at an object of study that you really want to try understand better. You want to know how to explain it. And so you gather data about it, and you try to come up with a theory that explains some or many aspects of that thing that you're trying to study. So you're starting with something concrete, You're gathering data, and you're coming up with theory, which is something abstract that explains that object of study. Now, when you're doing engineering, you're doing something a bit different. You're starting with something that is a bit vague, possibly a bit abstract. You're refining that, and you keep refining it into maybe a specification, and possibly you end up with a concrete software product that you can use. And so I think you can see the parallelism between these two activities. On one, you start with the concrete and you end up with the abstract. In the other, you start with the abstract and you end up with something concrete. When you're doing research in engineering topics, most of times you're not able to stick with one of these two phases. You have to do a bit of science and then you do a bit of engineering in order to show that the theory that they've come up with is really something real. It's an accurate depiction of how the world works. In our area, what I'm talking about when I talk about an object of study, that's usually, well, a piece of the system, an approach, an algorithm, how teams work together. So it's one of those things that we work with all the time. And this kind of research in engineering, is something that I'm going to talk about in an example that I'm going to give of DevOps research. So possibly a lot of you have, or some of you have heard about the DORA project. That's actually a research project. You had researchers working on it. You also had engineers working on it. And that's a project that was very, I'd say, impactful in the industry, in the sense that it was the Accelerate book that came out of it. Some of you might already have met it or read it at some point. There's the State of DevOps reports that come out every year or almost every year with the new insights that this team of researchers finds. And then, in fact, they were so successful that, well, I forgot to mention one thing. What are they doing, actually? They're asking companies, asking professionals, what is the reality? And what is the reality in terms of the company that they work for? They try to assess some things that they relate with that company being more performant or that team being more performant. And so some of the insights that they give us is what characteristics of teams and of companies make them be more performant than others. So that's what they try to find out, okay? That's what they're interested in finding out. But there are, in fact, many other researches being done every day around DevOps. And I won't go into details. I just wanted to give you that one example. But I'm showing you these two figures that I got from a research article. And what they show is the number of publications that have been coming out, research publications on the left, that have been coming out around DevOps topics. And so we see that around 2015, there was a bit of a boom in work on this area. And this stops in 2018, but I'm sure it continued. The paper was done in 2018, but I'm sure that it continued in this trend. And on the right here, we have books on Amazon. So you see a similar trend there, of course. So if you look at those articles, I'm sure you'll find some pearls of wisdom there. Not on all of them, perhaps. Maybe you're not interested on all the topics that they address. But there are some things that the software industry at large doesn't know that well. And they could benefit from it, for sure. So now I'm going to try to focus a bit my talk on what are the topics that us here at the Faculty of Engineering have been most focused on. And I kind of was able to fit this into these three research lines over here, but there are others that don't fit, the other works that don't fit here as nicely. But in sum, I would say that we have this set of works that are mostly interested in improving the developer experience around DevOps. And that's works like improving how well a developer can create a Dockerfile. Does a developer trying to create a Dockerfile has the right tools in order to do that efficiently? And I'm talking about Dockerfiles, I can talk about container orchestration and other kinds of tools, okay, around containers. Then we have some other works that are related with microservice architectures. And we've been focusing here on how do we decompose monoliths into microservices. What's the right practices? What's the right tools? What tools can we provide, new tools with novel approaches that can improve this process? And even if you are not trying to decompose a monolith, what are the right practices to build a microservice architecture? And then, I'm talking about practices, right? One other research line is about patterns. And that's a very good way to document practices. And we've been writing patterns for a bunch of different things within cloud native systems and DevOps, which you'll hear about in a few seconds, okay? So I'm not really trying to go into detail here, just giving you an overview of the kind of work that we do. And of course, there's a few results coming out of this work. Some of them are research articles, others are events that we've been organizing around DevOps topics, and others are tools. And I'm guessing that maybe that's the most interesting thing here for this audience. We're not going to talk about all the tools that we've been developing, but we're going to be talking about some, and we're interested to know what you think about them. So to wrap up what I'm going to say in this intro to these works, just like to leave you a message, which is, if in the end of these presentations you think, well, that's an interesting kind of work, that's something that I would even like to try doing, a bit of research, there are a few ways to do that. You can enroll in a master course, and there's always a little bit of research in a master dissertation. If you're willing to do a longer journey, a 4-year journey, and take a PhD, then there's a chance to really dive deeper into research. And there's a few reasons that you might want to do that. You have some fun in the process on a topic that really matters to you. On the end of the 4 years, you're supposed to become a leader on that one topic, an expert on that one topic. And you improve the world in something that really matters to you, because you're trying to do some work on that one topic. Obviously, you chose that topic, you care about it, and you're improving the world a little bit on that topic. There's other forms of collaboration with the industry. If you don't want to lead research, but you want to be involved in research, then there's empirical studies that we often do. Sometimes in DevOps Port Slack, I've been challenging some people to participate in these studies, but not announcing all of them there. If you're interested in participating, reach out. And there are other forms of collaboration, projects that we have together with companies sometimes. So let us know if you would like to work with us. And I might be giving an idea that this is me doing all of this, and that's completely wrong, okay? So there's an entire group of people working with me on this kind of topics. These are some of the professors there were actually students at some point. They're now professors. So there's a lot of things to do. And that's where I wrap up my presentation. And I invite to stage some of the people that I've just showed their pictures there, that have been working on more specific topics, and they'll be talking about in a bit more detail on what they did in the context of their master's dissertations. And we'll start with Paulo.
All right, so good afternoon, everyone. Okay, so good afternoon, everyone. Before going on to the presentation about DevOps patterns, I'd like to start that I am Paul Marques. I just recently finished my master's in informatics and computing back in July. And if you want to reach out to me, there's my contact, my email, and my LinkedIn if you want to message me about. So, a little bit of context behind this. DevOps, as we all know, it's pretty much growing as a topic of research, as a topic of enterprises adopting it, and as a consequence, if you go online and search for DevOps practices, there are a ton of resources out there that you can use to try to see what are the best practices or not. So, but we noticed there were a bit of problems with those resources. The first one was most of those resources were not detailed enough. So if you come to DevOps as a bit of a beginner, you might read them all and be like, okay, so what really is continuous integration? What is automate your deployment? So we sensed that was the lack of detail there. On the other hand, we saw some more detailed resources, but we saw a bit of bias in them. So some companies that are related to tooling in CI/CD tools have posted their guides on what they think are the best practices and whatnot. However, we felt that was more like a bias towards their tools, so the best practices would be using their tools with those practices, and not more independent approach and saying, okay, if you adopt these practices, you have all these benefits, but you lose on some of these, which if you have monetary interest in that, you will not say it. So that was a bit of our context behind, and to tackle this, we first decided to study existing DevOps practices, and then we decided to document them as patterns. So patterns basically are good solutions to recurring problems. And for those patterns, we decided to evaluate the consequence of them in a case study within our organization. I'll go a bit further into detail what patterns look like later, but this is pretty much what we gathered. So we call them foundational patterns because we decided to focus mostly on the patterns that most of the literature, both scientific literature and lay literature like blog posts and websites, agree that were part of DevOps. So starting from the top left, we have version control everything, which in a nutshell is everything you need to run and operate your software must be in version control. This includes the application code, dependencies, infrastructure code, infrastructure configurations, application configurations, and so on. Then we have continuous integration. So continuous integration, you should get a large feature and split it into incremental changes, and those changes you should run them against some suite of tests to get faster feedback on those changes. Then moving on, we have the deployment automation. So that's pretty self-explanatory. So deployment automation should automate your deployment process as much as possible. Then, moving on to the left a bit, after you deploy your software, you have the need to know how it is doing in the production environment. If there are some outages, if there are some downtime, some degraded performance. And that's where monitoring and observability come in. So you should have the tools to go to check on the health status of your software. Finally, we have cloud infrastructures, which pretty much brings on all the benefits of using cloud, like availability and so on. So I don't expect you to read this, it's a lot of text, but a pattern structure pretty much looks like this. So we first have a context. If this pattern, that helps us to see if this pattern is adequate for us to compare it against our context as well. Then we have the problem. The problem is just what the pattern tries to solve. Then we have the forces. The forces, the best example of forces I can think of is the trade-off between costs and performance, for example, in some solutions. We have to balance both. There's more forces usually in patterns, but that's pretty much how they work. You have to balance and find a sweet spot on them. Then we have the solution. So our solutions usually are a bit abstract, so you can use in more different contexts, not just a specific context. But we try to provide enough detail so if you read it, okay, you can deduce immediately how you use this solution in your context. Then we have the consequences of a solution. Usually, we try to keep both positive and negative consequences for most information possible. And then we have the weighted patterns. So this explains the relations between the pattern in question and others that were present that the figure I previously showed. Finally, we have the matrix that's a bit different than most patterns out there, not in the DevOps context, but they make sense in the DevOps context, since you have to keep in mind that you need to continuously improve your solutions. So how do you improve without knowing how good they are performing? So that's why we suggest some metrics for patterns. Okay, moving on to the case study. So we conducted a case study in an organization where we implemented some of the patterns, and in the end we conducted a survey on the professionals from that organization and asked them if they agreed or not with the consequences. So in version control everything, I'll not explain for you to read all the consequences, I'm just trying to point out maybe one or two. The last one, that's a bit more debatable, it was when changing teams, it takes time to get used to the new version control strategies. So they felt that it was a bit debatable, a bit towards they felt it would take a bit of time to adapt, but some debate in there. As for continuous integration, the ones that stand out the most are the negative ones that they discussed. It is more complexity when you have to break down a larger feature into smaller increments. And they felt also that there was more complexity by having to maintain and create and maintain a test suite. Finally, for deployment automation, all the consequences that were suggested, the professionals agree with all of them, so there was not much discussion on that. And okay, so to sum up a bit and put this into like, what's a good use for this outside academia? So patterns are a good way to get familiarized with a new topic. So if you are a beginner to the DevOps field, or maybe you're just not a tech guy, maybe you are from management and you have to know how your team or your company is doing in terms of those practices, patterns are maybe a good starting point for that. Then it was mathematics that lacked on the formal scientific literature, so he tried to address that. And finally, we try to be impartial in terms of our patterns and try to provide both the good and the bad consequences of it. And this is my lightning presentation.
Is there also room for questions?
It's in the end, I think, right?
Yeah, so we'll just continue with the content. Okay? So, hello everybody, my name is Carlos, and I just finished a degree as well, like a month ago, here in the Faculty of Engineering. And I'm starting a position as a backend developer in the Netherlands at that agency. So there's my contacts if you have any questions by the end or if you just want to contact me. I'm going to talk a bit about my thesis, so it's all about cloud monitoring patterns. And as you see, recent trends in cloud and microservices adoption have been kind of changing the way we organize and architect our applications, right? So things are getting more complex, a bit more distributed, and you know, monitoring needs to change so we can actually still be able to monitor things properly. And that's what the industry did, okay? So they adapted and new monitoring practices emerged, and most of those practices, as you may see, really depend on the context of the company and what they pretend to achieve. And they can most of the times also be reflected in tools. So if their company adopts X tool or Y tool and they do whatever they want to. The problem with these practices is that they're not always evident. So here's the deal. If company X just around the corner uses certain practice, that doesn't mean that we can just automatically use it, even if we know that they're doing it. They are difficult to learn and hard to communicate, mostly because there's no standard format or like definite level of detail that all of the practices share. It's really hard to understand what's something when you know you can really just transfer knowledge from place to place. And even worse, we didn't really find a lot of research regarding the topic, so we went forward and we decided to formalize these practices as design patterns. Okay, Paul already explained design patterns to you, so I'll skip this part. What we did was basically study whatever existed, so monitoring practices and design patterns that already existed out there in the literature. And then we developed our new design patterns. We also just picked some and enhanced them and kind of refined them a little bit to give some more detail. And then we went on to evaluating these new patterns that we proposed in our thesis with a company here from Porto called Consulting. That we developed a thesis with them and we ran a case study with a project there. And to finally the big objective of this whole research was to get a catalog of patterns for monitoring cloud applications. And the cool thing about this catalog is that it's really useful for practitioners and the industry overall. Most of you may already use or have used design patterns, and you know that it's really cool to pick a pattern and try to apply it on a context that really wants it, that really needs it. And that said, we went on with a literature review. I'm not like showing everything here, of course, but that's some of the most interesting works, especially the books. I think you guys will really enjoy these books. The first one, Building Microservices, from Sam Newman, got the second edition like 1 year ago. It's very up to date. It's very cool, very practical, very easygoing. So it's a really cool book that I recommend everyone to read. And on more on the academic side, we also have this PhD thesis from Professor Tiago Souza, entitled Engineering Software for the Cloud, a Pattern Language. So it proposes a bunch of patterns towards everyone that's developing or just maintaining something on the cloud. They're very detailed, they're very like meticulous, and it's really interesting, and they are very good patterns to apply in practice as well. So after everything, we ended up with 11 design patterns, okay? And that's them here. Let's just dive into it. So we started with the logging patterns on the left. So we have audit logging. Basically, it suggests that you should use logs to record user activity, either for auditing processes or just helping and supporting customer service that can really understand what the user did. These logs are immutable, and so you can save them securely, and they actually have legal value. Another pattern called standard logging is kind of straightforward. Essentially, as many teams work on different parts of your application or in different services, it's good and you should have a standard format for all your logs so they can be easily exchanged and even consumed by third-party applications. Log sampling is kind of straightforward as well. So, logs start to pile up as the application grows, and at some point, it's really a pain in the ass to manage. So, you sample logs in some intelligent way to maximize the information you get while minimizing the amount of logs you need to store. All these patterns here, they kind of support distributed tracing in the sense that commonly tracing is based on information that's passed through logs. So I'll just explain the pattern here. Distributed tracing consists on understanding the way a user request flows through your application, okay? Most of the times that happens through logs, they get a correlation ID, and that thing gets passed on. And you can then understand where the request has been, how long it has spent on each part of your application, and even some events or some extra information that you want to stuff into it. It's really important. It's a very common practice that's emerging, and there are very many tools around it. You can also extend this kind of tracing with some tracking of relevant events. For once, you have exception tracking. So exceptions are critical error. Right? If anything goes wrong and there's an exception, we want to tackle it right away. So it's important that you have a specialized system to tackle exceptions that handles the application, that ensures the stack trace is fully saved, and you can actually get on with it and troubleshoot your application from there. When it comes to deployment tracking, as deployments are major changes in your system, it's most likely that an error has been caused by a deployment. It's always cool that if you can understand where exactly in time did you make some sort of mistake, you still find out. So if you track your deployments, you can then correlate other metrics of the system, and we'll get there, with the deployments themselves and find the source of the problem. So in this column here, I already talked about these two, but all these patterns, they feed into metrics, okay? They're basically event generators. You can generate information out of things that are happening. And so let me just explain really quick these two up here, liveness self endpoint and readiness self endpoint. They're very similar. Our service or application, they will expose an endpoint that, for once, either in the case of the liveness self endpoint, shows the liveness status of your service, so if it's crashed or not, essentially. And if it is, you can automatically restart it and everything will go smoothly, hopefully. And when it comes to the readiness self endpoint, it's more about, it's really ready to reply to user requests. So it may be up, but it might still need some background processing or some dependencies. So you kind of still need to wait for it a little longer before routing traffic to that service. When it comes to synthetic testing, it's quite simple. You grab a bunch of your tests, or all of them if you can, and from pre-production stages, and you get them running periodically in your production system. Because at the end of the day, that's what users are using. You want to keep your system. You want to be sure that it's still behaving as expected. Finally, last two patterns, application metrics and infrastructure metrics. It's kind of straightforward. We collect, we manage, and we store metrics so we can actually take more informed decisions on our system. And it comes in two levels. So either application, which is mostly eye-level stuff, right? Like the number of logins, number of visualizations of a video, or even like throughputs of user requests per minute. And we can also, and we should also, store infrastructure metrics, which is mostly related to the machine itself. So CPU usage, memory usage, they're not necessarily the problem, but they are good symptoms that something might be wrong. And yeah, that's it for the patterns. I didn't dive into too much detail, but patterns are really helpful for practice, okay? They're practice oriented. So I think that if you read the patterns, you pretty much learn something. They go into much detail regarding trade-offs and things that you should consider when you're adopting something. And they're not that hard to adopt because most of them go into tools, okay? These are just some that we use and that are mentioned in our patterns. So yeah. Because the thesis was developed with a company, it's actually under embargo yet. So we're actually looking into a way to make this whole pattern catalog available. As soon as we get it, possibly in a Notion file, we will text you and let you use them publicly and free. And now it's time for Tiago to talk about his file.
Hi everyone, so bear with me in my English because I didn't know it was supposed to be in English, so bear a little bit with me. So I'm going to talk about service mesh. First of all, hi, my name is Tiago Maia. I'm the weirdo of the group because I have a master's in software engineering, not software informatics, so I'm sorry. Don't be your colleagues. Currently I work at a company called Farfetch. And currently one of the topics that we're working on are containers, orchestrators, and declarative pipelines. But that's not what I'm going to talk about here. I'm going to talk about service mesh. Before I talk about service mesh, it's important to understand how this started. So what is the big picture? What is the problem? So as you all may know, microservices is an architecture pattern that is very adopted nowadays. And people are using it because it has a lot of advantages, right? Teams are now independent from each other. They can deploy it whenever they want. It's much better to scale the application, the service that you only need. But it's not a silver bullet for all your problems. So what's the big problem here? Before we had a monolith, right? And the monolith for your application had all of these features that needed to work, such as security, such as resilience, such as observability and monitoring. So this is what we'll commonly call cross-cutting concerns related with communication. These problems, now that we are using microservices, need to be replicated for all your services. Before we had a monolith, you only create their logic, and now I have microservices duplicating the logic everywhere. So this is a commonly microservice application. We have here 3 services, A, B, and C. Usually nowadays, different services have different languages, like here, Python, Node, Java, and each service has its own stack of dependencies, of frameworks, of libraries, right? You will need security, you need load balancing, you need service discovery, you need and many other stuff, right? And now with the service mesh, what you basically do is you remove all that logic out of your services and you use a service mesh. So what is a service mesh? A service mesh is an infrastructure layer that is configurable, and the main objective is to remove the cross-cutting concerns out of your service. So your developers can only focus on business logic inside of your application. So infrastructure layer that removes cross-cutting concerns related to communication out of your services. So why is this a problem? Why is this important to document and to talk about service meshes? First of all, it is a recent topic, especially mostly 2 years ago. It was a very hot topic. We still have a lot of lack of information. And another big problem is companies want to sell their tools. Service meshes are mainly distributed by companies. Companies develop service meshes. And when I'm trying to sell something, I'm going to talk very good about my tool, right? My tool is amazing. My tool has all these cool features and powers. But like everything else, it has pros and cons. This is just a cool survey that I found on the Cloud Native Computing Foundation. That about 250 people that participated in this survey, 70% were already using service mesh. So I'm going to talk about those patterns that I documented. Very small smaller detail. So a service mesh, as I said, it's a way to remove cross-cutting concerns out of our services. So we have basically two main components, data plane and control plane. The control plane is where the user interacts with the service mesh to specify the configurations needed for your services to work on those cross-cutting concerns. So we have observability, we have security, we have resilience. Imagine you want to say that your services are supposed to do a canary deployment or a secret breaking pattern, right? You can do it by specifying to the control plane, normally using YAML files. And then the data plane is the plane that makes sure that your services are respecting the configurations that you pass by the control plane. This is just an abstract pattern of the service mesh, and then we dive deep into two specific implementations of the service mesh. So one of those implementations is the sidecar. The sidecar basically means that on the data plane, we have a sidecar for each service. So if we're talking about the Kubernetes context, orchestrator, we have our services deploying on the pod, right? Each container has its own pod, and next to each container on its specific pod, we deploy a sidecar container. This sidecar makes sure that all the traffic that is going to the services passes by the sidecar. It makes sure that your configurations of cross-cutting concerns are respected, and it acts basically as an independent proxy for each service. Few companies that use this approach for a sidecar service mesh, Issue Linker Console. The most known is Issue is open source, and for your people that are Amazon lovers, AWS also exists for people that like Amazon. This is a very common practice sidecar approach for big applications that require their services with specific configurations for independent service. So imagine that I need for my service a specific secret breaker, but my pod B doesn't need that. I don't need to do that for the pod B, right? I can do specific configurations for specific services. The node agent is the other approach. The difference is that you only have one agent per node, per machine, and then it enables that your configurations for the cross-cutting concerns are also respected, but it's one agent for the single node, right? So the same concept as sidecar, but you don't have a specific proxy for each service. The proxy acts, the node agent, the proxy acts for the single node, for all the nodes. So all the services inside the node need to use the configurations on the node agent. You cannot specify specific configurations for specific services. So on one hand, you save resources, right? Because you only deploy the node agent. On the other hand, you lose configuration. One of the tools that uses that is Traffic. Maybe you know Traffic because of the proxies. It's a very known proxy, but it also has its own service mesh, Traffic mesh. Shared communication library. Well, this problem of the cross-cutting concerns is not new, right? Microservices is a very old pattern. So people used to have a solution for this, and that's libraries. Netflix, for an example, has a bunch of libraries that they use to tackle their cross-cutting configuration problems like Ribbon or iStreak. And you basically create your features, create a library, and it's used on the different services. A service mesh team. This is a new concept that we created that basically means that in a company you should have a specific team that works for the service mesh. This team has two objectives. First of all, to agilize the process of developing features for the service mesh, helping developers to make the process easy to the service mesh, and on the other hand, to remove a dependency. So let's go back a little bit. We have a monolith. The monolith, every team is dependent on each other, it's a problem. We go to microservices. Teams, they do not depend on each other, that's good. And now we have a service mesh. Now all the teams that won't use the service mesh are dependent on each other because they need to apply configurations. That's a big problem again, right? And then the service mesh team, what it does is to remove that dependency from teams to teams, and now all the teams depend on the service mesh team, removing and diminishing, sorry for my English, the number of dependencies. Last pattern, multi-cluster service mesh, is a pattern specifically for increasing resiliencies and save resources. What it means is that in a big company, when we have a bunch of clusters, maybe from different data centers, we have multiple clusters using a service mesh, so we can use a single service mesh controlling all those clusters. What it enables is that in terms of resiliency, if I want to, for example, increase the version of my Kubernetes, I need to shift the traffic from one cluster to the other with one button. So I can shift the traffic from one cluster to the other, increase the version of Kubernetes, and then change the traffic again, increase the version of the other cluster. This enables a zero downtime upgrade. The other thing is that you can use a single control plane to control different clusters, so saving a little bit of resources. Putting it to practice. The bold question, is the service mesh for everyone? Possibly not. Is it for your context? It depends. Service mesh has positive consequences and negative consequences. On my master thesis, I enter into much more detail about the consequences, positive and negative, and you're free to go and check it out. So it's not only positive consequences, it also has negative consequences, but it's a good improvement, on my opinion. Thank you.
Okay, so hi, I'm David. I completed my master thesis here in informatics and computer engineering in 2020, and since then I've been working as a backend engineer at Samazi, which is a company in the tech industry. So basically, we process lots of user data and cluster those users into groups. So just to give you a little bit of context, raise your hand if you've ever used Docker. Alright, so I guess most people here are familiar with Docker at least. So you know that if you're developing containerized applications nowadays, basically you're probably going to use Docker, and therefore you're probably also going to write a Dockerfile for your containers. Here is a little bit of the development process that usually goes with developing a Dockerfile. So first you start with the code. And the code is a Dockerfile, which you build into an image, then instantiate in a container. Then you may want to take a look at how the container is doing, or if the services are running and if everything's fine. So you may want to open a shell into it, analyze it, and then iterate it, going back to the code and repeating all this process. So taking a look at this concept of live programming. So live programming is a concept where basically, do you know when you're editing a code and basically if you forget a parenthesis, you immediately get a res quickly line telling you that there's something wrong there. So that's some form of liveness, because you're writing code and you're getting the feedback from your development environment as you're writing the code. So basically we were thinking, how could we apply this concept into Docker files, so that we can get some live and rich information about the Dockerfile that we are building. So that's the question that we posed. So how can we use live programming to improve the development process of Dockerfiles? And from this question came Dockerlive, which is an extension for Visual Studio Code, which automatically provides feedback to the developer about the Dockerfile that he's writing. And basically what Dockerlive does is that it takes that process, that development process that we just looked at, and basically does a bunch of those steps for the developer so that he gets all that information without ever leaving the IDE. So just to show you a bit more concretely how this works, I have a little demo here, which I'll show you. Right, so here we have a Dockerfile, and as you can see, we have like a res quickly line there, and basically if you look at it, that start file.js has a typo, so it's missing an I. So the extension tried to build the image, but it couldn't because of that error, so it underlines it for the developer. So once we fix that, you can see that the image now builds and the container is now running. So you can see also that above each line, you can see how long each instruction took to execute, and how big, how much space does that instruction add to the final image. So let's keep going. Right. So you can also see what the current OS is, what the OS is in the container. So in this instance, we are using a version of Alpine Linux. Right there on line 7, you can see that there's a yellow squiggly line, and that's there because Dockerlive detected that you defined that environment variable explicitly in the Dockerfile, but it got changed at some point by some program that was executing. So it may not be an error, but it's kind of a weird behavior. So maybe you want to tell the developer about this. Right, so something else that you can also do is see which processes are running inside the container. So in this case, this container is just a simple Node.js program, so it's just running npm and Node. And here you can see also the performance statistics on those of the container. You can see the CPU, the memory, and the network input as well. And you can also open a shell directly to the container there. You can also see the changes that each instruction made to the file system inside the image. So basically, each instruction may cause a change in a layer of the image. So you can see all the layers here and all the changes that it does. So you can inspect the entire file system here. Yeah. So we've put this everything to practice using the extension. We've done some empirical tests with users, and basically we found that the users, developers who are using this tool are able to find problems faster and iterate faster in their development. And this extension is also available online. It has like 2.4K of downloads, so it's pretty has some good acceptance from the general public as well. So yeah, feel free to try it out and reach out to me if you have any questions as well.
So, hello everyone, thank you for coming. For this last presentation, I will talk about Hermit. I will introduce you Hermit. My name is João Maduro. I completed my integrated masters in informatics and computer engineering in 2021, and since then I've been working in Pharma, where I work in software solutions for gaming machines, like the ones you can find on casinos. This only using native and embedded technologies. You can also find here my contacts, but to start this presentation, I will introduce you the context to explain why we needed to create Hermit. So, with the advent of Docker, we found it more easy to migrate existing services to containers, which in turn made us possible to deploy services in other machines. However, this process is not automatic because we still need one manual step, which is to write the Dockerfile. So the question is, can we automate that step and make the entire process automatic? Well, if we have that tool, we can make this entire process, describing this image, automatic. We have a tool, a Dockerfile generator, we could generate our Dockerfile, so we can build our image and then run our container. So, we want, just like described here, we want the tool that is able to generate Docker files to a given software repository. It studies the repository and it generates its respective Docker file. And that's how Hermit appeared. We can see here the design of the tool, describing basically its workflow. In the first step, the tool analyzes the project, first statically its source code, and then dynamically its execution in runtime, which means it's tracking all of its system calls, its interaction with the operating system, and tracking all the necessary information. After that information is collected, we supply that to the data inference module, which will infer every necessary field of a Docker file. First, we try to infer the language, which will be necessary for the following steps, like the base image. We may want images more appropriate for null projects or images more appropriate for Python projects, etc. Then we fear all the necessary dependencies, like the dependencies that we install with the package manager of the operating system, for example, apps for Debian-based operating systems, and then the dependencies that we need to install with the package manager of the language, for example, npm for JavaScript projects. Then we fear the network ports that the Docker container must expose, and finally we fear the entry point so we can start our service. After all of this information is in fear, we can then proceed to supply it to the Docker generation module, which will convert all of this information in the respective file. All of these modules were developed with the objective of making it easier for other researchers and developers to replace them with alternatives proposed by them. And besides that, a fun fact is that the name Hermit is based on hermit crabs, which are animals that try to grab the perfect shell that fit their body, just like we want perfect containers to fit our software. So, this is an example of an execution of Hermit. First, we ran our tool with the process, and we can give it a timeout. And in the first step, it tries to detect all of the files used. In this case, it's a JavaScript project, and it only uses JavaScript files. After infusing the language, it starts the process and tracks every system call. All of these long lines in blocks are every single system call and their arguments. After the timeout is exceeded, we can enter in the inference step, where every single package is being detected. It should be noticed that Hermit will exclude the packages that are already included in the base image to avoid the unnecessary step of installing a package that is already installed. Finally, it will display all of the inferior information that will be converted in its respective file. This is an example, a simple example of a Dockerfile. We have the base image, we have the command to install all of the dependencies, and we have an entry point to run the service. And of course, we have the port that we want to expose so that the service can communicate with other services. Then, after we develop our tool, we conducted an empirical study to evaluate its performance. In the first image, we can see the performance of Hermit in generating Docker files. For this study, we grabbed 120 projects randomly from GitHub, and this is its success rate. More than 2/3 of the projects were able to get a Docker file successfully generated. 1/3 of the Docker files generated failed to build, and there were some of the projects that they missed 1 or 2 instructions so they could be successfully built. And one interesting thing is that there is an interesting project that could be work in the future that we may combine Hermit with Dockerlive, described by David, and we can generate the simple version of a Docker file with Hermit, and then using Dockerlive, we can iterate in the said Docker file to make it work. Maybe if we combine those two tools, we can make a tool with a better success ratio. Now, this empirical study compared the Docker files that we generated with the Docker files that were existing in those repositories. We compared a lot of statistics, like the dependencies, if the entry point was right, but I'm going to focus on the dependencies because it's one of the most important aspects of a Docker file. What this graph represents is that basically around half of the projects analyzed had all the dependencies successfully inferior, which means that it has a misdependencies ratio that is 0 or tends to 0. The other half had bigger values, like 40%, for example, 40% of the dependency is missed, which may mean that it's not a problem with Hermit. It may be a problem, maybe, it depends on the context, it may be a problem in the original repository that used more dependencies than it should really need, because the containers built successfully, the service was able to run. Maybe it could be missed in some point in runtime, or maybe that dependency is never really missed. It really depends in the context and in a project-to-project basis. And that's all. Hermit can be found in GitHub. It's open source and freely available to everyone. So I invite everyone to try out the tool and maybe help me make some upgrades to the tool. Maybe you can improve its success ratio. And if you want to find more about the tool, like for example, the empirical study that we conducted, the results that we obtained, and the tools that we developed to help us automate the empirical study, you can find all of that in the second repository, automatic service containerization. With this, we may be able to finally make the entire process of migrating existing services to the cloud more easier and more automatic, which is represented by this image, and Hermit represents that first step, like I presented earlier.